Hi, welcome to tutorial 4.1 part 1 on writing expressions involving strong electrolytes. So strong electrolytes is something we talked about in class, and on the next slide here you'll see what we mean by a strong electrolyte. Sodium chloride is an example of a strong electrolyte. What happens when sodium chloride dissolves in water is that we end up with these ions in a solution. The green here represent the chloride ions, and these purple are the sodium ions. So how does these very strong attractions get over? How are they overcome by the action of water? Water is polarized, and at this red end, that's the oxygen. There's a slight excess negative charge, and it can surround the positive sodium ions. And you see here's a bunch of water molecules that have surrounded a positive sodium ion. And here's another one down here, and a third one down there. And the water molecule can use the opposite end, that is the hydrogen end of a water molecule. Since the water molecule has two poles to it, that's the positive end. And that positive end can surround the negative chloride ions. And you see them here surrounded. These three chloride ions have been surrounded by water molecules. So how do you write this dissociation reaction? You say, starting off with sodium chloride as a solid, we can dissociate it or dissolve the material into two separate ions, sodium ions and chloride ions. This is fine and good, but this is slightly different than what we're trying to practice. Here's what we actually want to practice. Sometimes in a balanced chemical equation, when you balance the molecular equation, you're going to have three sodium chloride units shown like this. And we would like to show how the ions actually exist in the solution, the way it's shown here in this diagram. So if you had the expression 3 sodium chloride units aqueous, this is somewhat misleading because the sodium and the chloride ions aren't actually in any form attached to each other. They're not a solid. They're free floating. So that we have three separate sodium ions from the three chloride ions. And this is just kind of a bookkeeping thing. We're just going to want to try to be able to write this thing without making any kind of errors. So let's try a couple of these and see if we can do it. Here's an example. If someone said in a balanced equation I had the 6 magnesium nitrates as one of the products or reactants, how would I show the actual ions in the solution? So this here on the left, this white area, shows a picture of a unit of magnesium nitrate as a solid, and you're being asked to write, if you had 6 of these units in a dissolved state, how would you show them? You say, well, I'd have 6 of these magnesium ions, and that would also have how many of these nitrates? Well, there's 2 per unit, so 2 times 6 would be 12 nitrate ions. We would write it like this. 6 magnesium ions would be floating around independently, and then 12 nitrate ions would also be floating around independently. All right, so that's the first one. Let's look at this one here. Same kind of thing. I think the diagram is slightly confusing because you don't see these hidden carbons. So there's a carbon up here at the vertex and one down here. So this carbon has 3 missing bonds. So there's 3 hydrogens around that carbon. So that's CH3. And then over here there are no missing hydrogens, so that's just C with this double bonded O and another oxygen off to the side. So here's how we're going to write this thing. There's 2 carbons, these 2 carbons, that's the C2. H3, those H's are sitting at the end over here of this acetate ion. And then there's 2 oxygens, these 2 here. So notice this doesn't really show the structure, but that's how we'll write acetate ions. How do we show that in terms of the ions, the way they exist in a solution? We say, well, if there's 3 of these units, there'd be 3 magnesiums, and 2 times 3, 6 acetate ions floating around independently. So 3 magnesiums, and then 2 times 3 is 6 of these acetate ions. Let's do another one. This time there's 2 sodiums and a sulfate, and sodium sulfate. How would you write the ionic equation for 4 of these? You might find this a little confusing. So, well, wait a minute. Now, when I look at this formula, if I don't have this picture in front of me, how am I supposed to know when to multiply one of these subscripts by the coefficient in the front and when not to? You actually have to recognize when you have a polyatomic ion and when you don't. So you have to recognize that this is a polyatomic ion. So this 4 in the front means 4 of those sulfates. Here in the picture, of course, it's obvious because you can see them stuck together. But you have to recognize that in general, and that there are 2 times 4, 8 separate sodiums. In this course, we're only going to have polyatomic ions that are negatively charged. There'll be a few exceptions, the ammonium ion, for example, and I'll kind of warn you about those. So most of the time what you can do is say any subscripts that follow the metal ion, the cation, those you'll have to multiply by the coefficient, because you can tell in this case there's 2 sodiums for every sodium sulfate. But the polyatomic ion that follows, keep those in your mind together, so there's 4 separate sulfate ions. So here's the answer. 8 sodiums and 4 sulfate ions would be this expression written out long. All right, let's look at another one. Potassium carbonate. Again, there's a hidden carbon in the middle, but you can tell that's just a CO3 with a double negative charge. Again, straightforward, like the last one. 2 times 5 is 10 potassiums. In the picture, it's obvious. You're going to have 10 of these purples with 5 units of what's in the white, and 5 carbonates. So therefore, we have the answer. 10 potassium ions and 5 carbonate ions with a double negative charge. This one is easier. The only thing would again be at all confusing is you wouldn't be quite sure which of these subscripts you want to multiply by the coefficient. And the answer is going to be the metal. If it doesn't have a subscript, there's just going to be 5 potassiums. You can see it here. And that ClO3 is a group. So you don't multiply the 3 times 5 to get 15 of anything. Instead, it's 5 of this chlorate ion. So the answer is 5 potassiums and 5 chlorates. Again, the picture makes it obvious, but you're not going to see the picture on the quiz. This very last one is not a strong electrolyte of the same sort because it's not an ionic compound. We don't have positive and negative ions here that are simply being separated by the action of water. Instead, the water is actually separating the molecule itself. And this is only included kind of for completion's sake. We're going to see this when we talk about acids and bases. This is a strong acid, so water is going to actually pull this molecule apart, leaving us with the hydrogen ions and these chlorate ions separately. So what you do with this expression is the same as what we did with the ionic compounds. It's still going to be, in this case, 3 hydrogens and 3 chlorates. But exactly how we manage this when we don't see any ions to begin with, we'll have to think about that when we do acids and bases. Okay, so that's all there is to the PowerPoint. So what I want to do now is jump over to the website, and the reason is that when you practice this on your own on the website, the formatting is going to perhaps cause you a little bit of trouble. And so let me show you what I mean. The way you're going to write these expressions out by typing them in this input field here is you can't write it like this. So for example, if I said 4 sodium sulfates, you'd like to write 8 Na and then a superscript aqueous, with a superscript with a charge, plus 4 sulfates with a superscript 2 minus. And the problem is there's no easy way for me to, or at least I don't know the way to do it, for you to create a super or a subscript in these input boxes. So here's the kind of hack. This is the kind of thing that I came up with to solve the problem. I'm saying please leave a space between the sodium in this case and any charge you want to show. So if you want to show this as a superscript at plus sign, just leave a space and I'll know you mean superscript. But that means you got to kind of be careful about these other spaces in here. So leave a space between these plus signs. I'm not going to treat those as superscript, but then leave a space again between the sulfate and the double negative. But you can't leave like spaces between these numbers and these ions. So it's a little bit of pain. I hope this is good for you to still practice. I couldn't do any better than this in terms of the formatting. But let's try a few of these so you can see how it works and see if you can gain some kind of confidence with it. All right, so I see 7 of these units of rubidium sulfate. So how many rubidiums do I have? I have 14. So 14 rubidiums, and then I leave a space. Then I put my positive charge, and then the aqueous. And now space plus space, oops, not plus, and then SO4 space 2 minus aqueous. And I think I forgot how many sulfates. There's 7 of these sulfates that I have to put inside here. I think I've got it now. Let's see if this is right. 14 rubidiums and 7 sulfates. Yeah, that looks pretty good. All right, so it's going to now show you, I can, behind the scenes, I can put in the superscripts and subscripts. I just can't get you to do it in the input box. So you'll see the answer down there to help you. Now let's try just another one so we have some confidence. How many sodiums do you see here? 2 times 5. Now notice I'm going to multiply this subscript by 5 to get 10 sodiums, but not this next to the carbon because the C2O4 itself is the group, and the only subscript here, if you want to think of one, is a 1. We have 1 oxalate ion sitting there. So the answer is 2 times 5 is 10. No spaces, Na, space with a plus, and then the aqueous. Now I leave a space to show I have another ion, another space, and then I have 5 of these oxalates, C2O4. Now I need a space, 2 minus aqueous. So it's a little tedious to write this thing out. but this is then the answer. So notice when I wrote this thing out just now, I left a space between this small lowercase a and that plus sign. I left a space between that 4 in the oxalate and the 2 minuses, but no spaces in the other parts of the formula. So not perfect, not ideal in terms of formatting, but I think you get used to it. People have done it pretty well in the past, and it is helpful. It's a nice place to practice. On the regular quiz, it'll be a multiple choice, so you won't have to worry about formatting, but in terms of practice, that's how you do it here. All right, good luck with this. I hope it works out for you, and we'll practice together in class. Thanks.